welcome to another WJEC A-level physics question. This one was from May in 2010 and it was question 6 on that paper, and it's basically a motion under gravity and a velocity time graph question. So a stone's released from the basket of a hot air balloon, and this balloon is actually moving upwards, and that's an important point that we've got to remember. The velocity time graph describes the vertical motion of the stone from the moment it's released to the time it lands on the ground at 3.2 seconds. And we're going to ignore air resistance all the way through this question. That's going to come in towards the end of the question. For part A, we're asked to calculate the gradient of the graph and explain its significance. So when you find a gradient, it's always a good idea to make your line into a large triangle here. So I'm using the entire length of the line. And remember that the gradient is basically the change in the y divided by the change in the x. And here we've got y going from 4 at the start to minus 27. So that's a difference of 31. Now, I've got to be careful there because I've seen a few people think that that difference was 23. Difference in x is 3.2. Now, if we do that on a calculator, again, just think carefully that we don't need too many significant figures here. So 31 divided by 3.2 will give us 9.7, shall we say, meters per second squared. Now, technically, this should be a negative answer, but exam board aren't too worried about signs or number of significant figures for the answer, so I'll just put a little minus sign at the front just to be mathematically correct. And the significance of the gradient is that it represents the acceleration due to gravity. The second part of the question says, state the velocity at which the balloon was ascending at the moment that the stone was released. So when a stone was released, we can simply read off the graph here that the velocity was 4 meters per second. Next, we're asked to describe the motion of the stone between 0 and 0.8 seconds. So we're looking at the graph. Let's talk about it first and then we'll find something to write down. We're starting off with a positive 4 meters per second velocity. So the stone is initially moving upwards, but then that velocity reduces down to 0. So the stone is moving upwards, but with a downward acceleration. And it's a straight line, so it's a constant deceleration. So 0 to 0.4 seconds, stone moves upwards. With a constant deceleration. At 0.4 seconds, the velocity of the stone is 0, so the stone is at its maximum height. I'll just put 0 velocity in there to help explain that. And then 0.4 to 0.8 seconds. Well, now the stone is moving downwards, but it's still got that downward constant deceleration. Or it's an acceleration in this case because it's causing the stone to gain speed vertically downwards. Okay, next part of the question says, shade the part of the graph which represents the height of the stone above the ground at the moment of release. So if we think about what's happening between 0 and 0.4 seconds, our stone is moving upwards. At 0.4 seconds it reaches its maximum height. And from 0.4 to 0.8 seconds it starts moving back downwards again, or it is moving downwards again. So at 0.8 seconds it's back at its original height. So if we find this area from 0.8 seconds till the end of the graph, remembering that the area under a velocity time graph represents displacement, then we're going to have that distance that the stone has fallen from its original height all the way down to the ground. Now we could shade the entire part of the graph there, including this sort of negative, this small section at the start, so long as we remember to take this little section here, I'll mark it with a squiggle, just remember to take that away from the whole area. But I think it's simpler just to consider this trapezium from 0.8 to 3.2 seconds, remembering that the stone is back at its original height at 0.8 seconds. So various ways of calculating height, but they're trying to lead us into that the height is the area of that trapezium. We could use a suvat as well, for example. The area of the trapezium is half of the sum of the parallel sides. Well, this side has got a height of 4. If we just read across here. And the other side has got a height of minus 27. So we can ignore the minus signs for simplicity. So we've got 4 plus 27 times the distance between. Well, we're going from 0.8 up to 3.2 seconds, which is 2.4 seconds. So let's put that into the calculator. And we get 37.2 meters. And the final part of the question asks us to consider what happens if the balloon was actually also moving horizontally. So the balloon is moving horizontally at a steady velocity when the stone is released. State whether the stone will land on the ground, behind, directly in front of, behind, directly beneath, or in front of the moving basket, and explain your answer. Well, it's going to land directly beneath because the horizontal velocity is constant. And it's also the same as the balloon's velocity. And the reason that is why the horizontal velocity of the stone isn't changing is because if we go right back to the start of the question, we were told that we could ignore air resistance throughout this question. So let's finish off by saying this is because there's no horizontal forces acting on the stone. So you've got to remember as well that even though there's a vertical force acting on the stone, the force of gravity, the component of that force of gravity in a horizontal distance will be 0 because cos of 90 is 0. So once again, thank you very much for listening. Please remember to like and subscribe.